The end Permian extinction event occurred 252 million years ago, about 190 million years before the dinosaurs met their fate, and lasted for approximately 15 million years and was the most devastating known extinction event in the Earth's history. So much so that it has earned the common name the Great Dying. As evident by its name, it marks the end of the Permian period as well as the lengthy Paleozoic era and the entrance into the Triassic period and Mesozoic era. More than 70% of terrestrial life and 90% of aquatic life was lost, and an estimated total of 96% of life was wiped out over the course of this one extinction event. This is evidence for the collapse of ecosystems on a global scale. The organisms around in the Permian consist of marine life such as brachiopods, ammonites, bony fish, sharks, and rays. Plants consisted of gymnosperms, which produce cones to house their seeds, such as conifers and ginkgos do. Insects such as beetles and bugs also flourished. The main terrestrial creatures of the time were ceratopsids and synapsids, the predecessors to mammals. The pterosaurs also lived in the Permian. The Great Dying would wipe out most of such life over the course of the first 100,000 years of its length, especially affecting the synapsids. The ceratopsids would fill the ecological positions left by the synapsids and become the next dominant group, the dinosaurs. But what caused such a massive extinction? The most plausible and well-researched theory is volcanic activity of the Siberian Traps, a large igneous province, also known as LIP, meaning it was formed by flowing lava. Although chilly and calm today, they were once a volcanic hotbed. The entire roughly 7 million kilometers square surface experienced some form of volcanic activity. Whether above or below, particularly aggressive activity documented in basalt formations lines up with a little before the beginning of the end Permian extinction record. While the idea of lava spearing across the earth in a massive explosion wiping out all life instantly is dramatic, it isn't what the fossil record tells us. If that were to happen, life would be wiped out in one day, not the recorded 100,000 years. Ash clouds and release of toxic gases from the earth is closer to the truth, but measurements of lava output and corresponding release of gases does not seem to account for enough to impact the biosphere as the fossils tells us it did. So what exactly happened? To set some chemistry straight first, the reasons the volcanoes release toxic gases is due to extremely hot lava melting rock that contains halogens such as chlorine, bromine, and iodine. The high temperatures cause reactions in the rock to occur, and products such as methyl bromide and methyl chloride were released, as well as hydrochloric and hydrobromic acid. In other words, an eruption did not directly trigger extinction, but rather caused emission of gases, particularly highly reactive volatiles from volcanic heating of chlorine and bromine-rich minerals. Although greenhouse gases were released as well, causing global warming and ocean acidification, what makes the end Permian especially catastrophic was this extinction's unique release of high quantities of volatiles. Studies in some of Russia's diamond mines, such as Yudichnaya, examined xenoliths, chunks of solidified magma scattered far away from their initial eruption point. These xenoliths contain data about halogen concentrations from various parts of the Siberian Traps during its eruption over the course of the end Permian extinction, taking into account possibilities such as seawater enrichment of these regions, since the deposit and the trends of halogen concentrations while descending deeper into the rock and back in time, the amount of halogens in the mantle of Siberian Traps can be determined to have 125 times more chlorine, 625 times more bromine, and 100 times more iodine than other volcanic regions. Volatiles and sulfur would have to be released in extremely large quantities, including about 70% of all available chlorine, which cannot have been achieved in localized lava flow above ground. However, studies show that horizontal magma flowing beneath ground in branches called sills will have reached enough of the rocky deposits to release massive amounts of volatiles into the atmosphere. Geological evidence shows that the Traps experienced a three-stage process of volcanic activity, including a span of sill formation, that lines up well with the beginnings of biosphere instabilities. So let's summarize the three-stage process of volcanic activity. Stage 1. Stage 1 was an extrusive or above-ground lava flow phase. This stage had very little effect on global ecosystems, as shown in the fossil record of species lost. Initial eruptions occurred which led to fast-moving current of hot gas and volcanic matter that moved away from the volcano at about 100 kilometers per hour, followed by lava coming out of the ground. During this stage, an estimated two-thirds of the total volume of Siberian trapped lavas were in place. Many other such massive extrusive events are recorded in geological history, yet the majority were not associated with mass extinctions, which is why step 2 is much more interesting in understanding the cause of the Great Dying. Stage 2. Eruptions ceased and an intrusive or underground magma flow in the form of sills took over as a primary activity throughout Stage 2. This stage may have been caused by the above-ground lava forming a thick layer over the area, preventing lava from escaping and forcing it laterally. A spike in carbon cycle disruption and the start of mass extinction began in this stage as well. Stage 2 ended at around 251.5 million years ago, when extrusion of lava resumed, marking the beginning of Stage 3. Both extrusive and intrusive movement of magma continued during Stage 3, which lasted until at least 251.3 million years ago. However, the length of time the extinction lasted is significantly shorter than the sill formation period of 500,000 years. Carbon dating of the extinction that the most effective interval Siberian traps actively falls near the beginning of Stage 2, when sills were first starting to spread. On a connected topic, let's talk about volatiles and the ozone. Volatiles being released into the atmosphere would have not suffocated life by itself. However, the halogens such as chlorine and bromine are highly reactive. These halogen compounds were ejected high into the stratosphere, where the ozone layer is. The stratosphere ranges from 10 kilometers to 50 kilometers above sea level. At the 20 kilometer to 30 kilometer range is the ozone layer. Well, so how was the ozone layer affected? Through a catalytic reaction in the frigid stratosphere. Chlorine can react with ozone in a reaction such as the chlorine oxide dimer cycle, destroying ozone and turning it into oxygen. Such massive amounts of chlorine reacting with the ozone would have depleted it very quickly, especially because the chlorine is a catalyst and can go on to destroy more ozone. During the 100,000 to 200,000 year eruptive phase of the Siberian traps, large amounts of HCl were released, which would have caused a 33 to 55% of O3 depletion. In addition, during the eruption, large amounts of CH3Cl were added to the stratosphere. The CH3Cl and other organohalogens were released from heating of organic compound-rich rocks. The addition of this would cause 5 to 20% of O3 depletion. When all accounted for, meaning the combined effect of CH3Cl and HCl in the stratosphere, this combination would cause up to 85% depletion of O3 and an enormous loss of protective ozone. So what's the importance of this loss of ozone? Well, UVB light is prevented from reaching Earth by the ozone layer, as it absorbs its energy and decomposes into O2 and an oxygen atom. These atoms can recombine and go through the process again, continuing to absorb ultraviolet light. The destruction of ozone allows for more UVB light to get through, as there is less ozone to be absorbed, the shortwave energy. UV, or ultraviolet light, is short-wave light invisible to the naked eye. Its short wavelength means it's extremely high in energy and has the potential to cause destruction of many chemical compounds. This is the main reason why we put sunscreen. The chemicals in our skin cells, including our DNA, is otherwise pummeled by these waves. When vast amounts of UVB energy reach organisms on Earth, rather than causing ozone to decompose, it causes mutation in DNA. This can be extremely devastating in those organisms that normally welcome sunlight into their cells. For example, plants. The fossil record shows evidence of mutations which cause gametes to form improperly in the gymnosperm forests of the time. Mutated spores of plants indicated a failure of individual spores to separate and complete the normal process of development. These mutations have been identified in Permian sediments from a global range, areas from Greenland to Australia. Pollen mutations have been reported from Russia and northwest China, which is close to where the Siberian traps lie. Sterilization of most of the globe's forests is certainly enough to knock the biosphere out of equilibrium. Modern testing of this theory was performed on the columnar Mungo pine. The study exposed that to UVB concentrations 13 times that of a particular sunny day, both pollen and cones experienced extreme fertility loss. All the subjects under examinations becoming effectively sterile. The pollen lost its symmetrical shape, composed of two saci that allow it to flow through the air and properly orient themselves in the reproductive parts of other trees. The majority of pollen in the experiment group post UVB exposure was composed of more or fewer saci than normal, cones being malformed or unreceptive to pollen, while the subjects in this experiment regained their reproductive functionality after being removed from the experimental conditions. Permian subjects would not have had such circumstances. A particularly strong spike of UVB, or more likely extended high UVB exposure, would have quickly destroyed forests within a few generations, taking down the web of organisms they supported as well. Technology can give a detailed and complete picture of the event, sped up so that we might better understand what could have happened. Computer models run simulations of the whole process starting from cell formation all the way to resulting O3 depletion, to the point of a significant rise in UVB levels. The simulations test numerous possibilities, including the steps of volcanic activity and the required concentrations of chemicals. These simulations show that organohalide-rich rocks combined with organic material pockets within the rocks provide the best setup for catastrophic biosphere failure. The release of both HCl and CH3Cl in large amounts show a depletion of ozone of up to 85% in northern regions. To give perspective, only a little over half of that was lost during the hydrofluorocarbon crisis in the 90s. Through impute of concentrations of halides and the length of eruption required to sufficiently deplete the ozone, scientists would have found that a span of about 100,000 to 200,000 years of volcanic activity is required, a nice match to the three-stage process previously hypothesized. So, overview and connecting the dots. In all, the Siberian Traps volcanic activity is one of the best models for the cause of the most catastrophic loss of life in the Earth's history. Magma and lava heats halides trapped in rocks and injects these volatiles high into the atmosphere. These volatiles then react with the ozone layer, eating away at it until UVB light can stream in unabated and attack the genomes of plants. These plants, making up the majority of forests, mutate to the point of infertility, leaving a gaping hole in the ecosystem. Very quickly, the food chain collapses and life is lost on a massive enough scale to label it as the Great Dying.